Alrighty. So remember, if you have questions, please raise your hand and we're going to promote you so that you can ask them in person. If you do not want to ask them in person or like, I guess, virtually, post them on Slack. So there's one question from Chen. One second, Hao. Okay, you've been promoted, Hao. Feel free to ask your question.
Hi, excellent work. I'm Hao from Yale University. My first question is that it's about the security of I/O. So one benefit of using trust zone is that you could have this hardware-based isolation of the devices on SoC. So you could have some devices, for example, a true random number generator that lives inside the secure world and only the secure world could access to it. So, but if you only allow the NVisor to manage the hardware resources, it seems that the SVMs is unable to enjoy these benefits. So I'm not sure, do you have any thoughts on this?
Okay, thanks for your good question. And our design principle is to reuse the existing normal world hypervisor as much as possible so that we can keep the iSvisor, our TCB in the SCL2, keep small regardless of the NVisor's involvement. So we reuse most pyro-virtualized I/O in the NVisor. But for those devices that are directly assigned to the trust zone so that the normal world software cannot access its device, we can, our SVisor can support these devices and maybe pass through them to the SVM. So I think the SVMs can both enjoy the virtualized I/O and the dedicated devices in the trust zone.
I see. Thanks.
Oh, thanks.
Okay, if I have time, I have another quick question that is about the design of the SVisor. So it's a good idea to decouple the protection from the resource management. But I'm just curious, what is how do you know that you have moved all the data structures that related to the security from the NVisor to the SVisor? I mean, is there any method behind the design that you know that it is complete? I mean, the SVisor completely manages the security.
Okay, because from the high level, we can divide the state of the SVM into mainly three parts: the CPU states, the memory view, and the I/O data. And we can ensure that for CPU registers, the NVisor we did not expose unnecessary states to the NVisor. And for the memory view, the most important registers for the memory view is stage 2 page table. And for the I/O, we assume that the SVMs themselves will protect their I/O with encryption and integrity. So there is a more detailed security analysis in our paper. So we believe it is enough to ensure the safety of the data from CPU memory and I/O for the SVMs.
Okay, thanks.
Thanks.
I think Andrew was next. Andrew, feel free.
Hi, I know this is a slightly unfair question because they only published the spec for this mid-summer this year, so probably the spec came out after your paper was submitted. But I wondered if you could compare and contrast TwinVisor with the upcoming ARMv9 Realms extension. Have you looked at the spec for that? And if we have Realms, does it make sense to do this? Is there some reason to prefer one system over the other?
Okay, thank you. That's a great question and also a frequently asked question. And yes, before the submission, we are known about some technical details of Realm in ARM-CCA, but now we have concluded mainly 3 points. And first, Realm and ARM-CCA is a planned hardware extension for ARMv9, right? And it provides isolated and encrypted VMs, confidential VMs. But it also requires a low-layer system software for management, like a secure hypervisor, whose implementation is not included. So such dual hypervisor system may have the same challenges faced by TwinVisor, including the intrusiveness modifications to existing software stack and the costly word switches, etc. Thus, the proposed solutions of TwinVisor, such as our horizontal trap and fast switch, can also be used to target these challenges. And second, the new capabilities of the Realm and the ARM-CC, for example, the fine-grained memory isolation and the hardware memory encryption. These hardware features are orthogonal to our design and can enhance the performance and security of TwinVisor's implementation if this hardware is available. And finally, the TwinVisor offers an option of ARM-CC with much simpler hardware because as we know, the Realm extension needs a third stage page table in EL3. So considering that CC will not be available in another year or two, according to ARM's roadmap, and TwinVisor provides a realizable choice for existing ARM cloud users to enable confidential VMs.
Okay, thanks.
Oh, thanks.
Okay, I think Shudong has a question. He's from UIUC. Go ahead.
Yep. So my question is that how much modification you need to make to the existing software to implement TwinVisor, and how large is the TCB?
Oh, in our paper, we have shown the TCB, and for the Icevisor, our TCB, the C code and assembly are less than 6,000 lines of code, and for the trusted firmware, we only need to modify the trusted firmware less than, I remember, less than 200 lines of code. And for Linux, there is a bit more because we need to implement the split CMA and some other cooperative management. So I'm sorry, I didn't remember the exact number, but maybe 1,000 lines of code also.
Okay, so a follow-up question is that do you think it's feasible to formally verify the correctness of the TCB?
Okay, and we also mentioned this in our maybe in our paper, because this small TCB compared with some existing formally verified systems such as the stack KVM and some Certic OS. They have some of them have larger TCB than us. So we believe it is feasible to formally verify, but we need to refactor our code, because, for example, for the concurrency verification, maybe they only support the big lock, the global lock, but we may need to refine our code before the verification, and this may be our future work.
I see. Thank you.
Thank you.
Great. So this is going to conclude our discussion of TwinVisor. Thank you, Dingji, for that excellent presentation and answering all the questions.
Thank you, Professor.
Sure. Now we're going to move on to the next paper, which is Snoopy, and it's presented by the dynamic duo of Vivian and Emma.
Great. Actually, we already received a couple of questions. Maybe we can start with the first one. I also posted the question from Slack to our Zoom. So Dingji, can you see the question from the chat box?
Oh, yes.
Okay, the question is, in Intel TDX, there is the same mode, and you can run a lightweight VMM in the same mode. So what's the difference between TDX and the TwinVisor? Thank you. I also have the same question. So can you give your answer, please?
Yes. So thank you for your question. And basically, both TDX and TwinVisor aims to provide a confidential VM. And Intel TDX provides specialized hardware for confidential VMs on x86 platforms, while TwinVisor aims to retrofit existing hardware on ARM platforms to enable confidential VMs. And in particular, Intel TDX as a microcode implemented SIM mode in its CPU, as the question mentioned, and dedicates an Intel provided and Intel signed firmware called TDX module inside this SIM mode to enforce the security of the confidential VMs, while TwinVisor leverages existing trust zone and the SCL2 extension to run a tiny SVisor to focus on protecting SVM.
Okay, so I also have another following question is about, so you're working on the ARM, right? So
Yeah.
we already know that the virtualization actually are very mature for x86, this architecture. So I don't know what's the new challenge or the unique characteristics bring from the ARM world, if you compare to the existing virtualization or secure technologies, right? Can you comment on that?
Okay, first, because in existing cloud and ARM is becoming more and more popular because it's excellent performance processor ratio and a rich ecosystem. And unlike the x86 solutions, because both the confidential VMs and the normal VMs, they share a untrusted hypervisor, but on the ARM platform, the trust zone architecture makes us require the dual hypervisor system that have the we must put another hypervisor in the secure world rather than sharing untrusted hypervisor like the x86 platforms.
Okay, this is how the name come from, right? The TwinVisor. Okay,
yes.
That's a pretty good choice. Okay, there is a second question I also posted here. It's made by Chao Yiran, from master student from University of Science and Technology of China. His question is, what are the differences and advantages of the investigating confidential computing compared to the x86-based hardware platform, which you already addressed, right? And another one is, does ARM platform provide more features for researchers? And I think the second question is it's the new. Can you go ahead to address?
Oh, okay. Thanks Chao Yi for your good question. And ARM platforms may provide some different security features compared with x86. For example, maybe some they do have some different features. Maybe I don't know that if the tag memory on ARM or the some other features. But what we know is that the ARM is attracting more and more users to use them. So I think it is reasonable for us to focus on the confidential VMs on ARM platforms.
Okay. There is another question made by Abby Hijate. I hope that I did not mess up with the name. He said, nice work. And the question is, so the H trap will occur for every IO operations from NVisor to SVisor. The question is asked whether it is true. Please go ahead to clarify this.
Okay, thank you. And for every IO operations, if the SVM triggers an MMIO VM exit, it will forward this VM exit to the NVisor, so the H trap will occur in these IO operations. It depends on your VM exit.
Okay. The following question made by Shiwei Li. He would like to know, can the secure VM use the private virtual IO, that is one virtualization technology, such as the VirtIO? If yes, could you please give some hints how it can work in secure world? Please go ahead.
Okay, thanks for the question. And in our current implementation, our secure VMs in the secure world use the parallelized IO such as VirtIO. And please refer to our paper because we didn't mention that we use shadow PVIO as a solution to make it work for SVM. And from high level, we need to set up a shared, for example, the IO ring and DMA buffer for the SVM. and the iSwider is responsible to copy the I/O requests and the encrypted I/O data from the secure world to the normal world, and that's how it works.
Okay. So I'm also very okay. There is another question from this panelist. I will first let this question to go. Jiang Jianyu, please go ahead.
Hi, I'm Jianyu from Hong Kong U. So I have 3 quick questions. So the first is how many VM can TwinVisor support? So is it scalable to the number of VMs? Yes, this is the first question. And the second one is, can it support other architecture such as like RISC-V, or because I think there's maybe some hardware mechanism in RISC-V such as PMP, yeah. And yeah, and the first question is, can you compare it to like the AMD SEV, which provides confidential VM also? Yeah.
Okay, thanks for your 3 questions. And this is our second time to talk to have a talk. So the first question is that about the VM scalability of TwinVisor, right? And according to our design, there is no limit on the SVM's numbers because the our secure memory has unlike the AMD SEV and the Intel TDX, they have the per VM encryption key, and we don't use the per VM encryption key, so there is no limit on the secure VM numbers. And our data structures designed for the SVMs, they are per VM, so more VMs does not result in the bad performance. So I believe our evaluation also shows that we achieve good scalability for more secure VMs in the secure world. And the second question is compared with, for example, the PMP in the RISC-V platform, right? And yes, the PMP is somewhat like the region-based secure memory in the ARM platform. So I think our design can give a reference to how to design a confidential VM system on RISC-V platforms. Some differences is that currently the ARM trust zone and they divide the normal world and the secure world, but on current RISC-V platforms, we didn't see such maybe they do not need a dual hypervisor currently, but we are also focusing on how to design a confidential VM for the emerging RISC-V platform. So maybe this will be our future directions. And the third problem is compare with the AMD SEV, right?
Yeah,
and,
yes.
And the AMD SEV, they deploys a secure coprocessor with its dedicated memory in the CPU to take care of the confidential VMs. So the memory, such as the encryption integrity checking, and are all done by this dedicated CPU coprocessor. But this is an entire hardware scheme because maybe the cloud providers or the vendors are not easy to modify and upgrade the coprocessor. And there are actually many papers published on maybe security and SMT talking about maybe some vulnerabilities in AMD SEV's coprocessor. However, and TwinVisor choose a software shim layer, and which has a better flexibility and is easier to be updated and verified.
Okay, but my understanding is that ARM trust zone does not provide any memory encryptions, but MDSEV provides memory encryption for confidential VMs. Does it mean that TwinVisor is not as secure as MDSEV?
Okay, maybe you want to know the impact of lacking encryption and integrity. Yes, the hardware memory encryption and integrity are used to defend against hardware and physical attacks such as replay attacks. But it is a trust limitation because from hardware level, it does not support such operations. But we argue that it is reasonable to for today's cloud because software attacks happen far more frequently than the hardware attacks. So we argue that it is reasonable to focus on the software and remote attacks. And maybe we can take the Facebook's outages on October the 4th as an example. The Facebook network has down for several hours and they spent several hours to get into the data center. Even their system administrators cannot get in physical touch with their machines. So we think it is okay to focus on the software stacks. And if the future hardware of ARM, for example, the ARM CCA, it supports encryption and integrity checking, it can apply these features, and the TwinVisor can also benefit from such architecture features.
Okay, thanks a lot. That makes sense.
Okay, thank you. Thank you for the question and also thank the answer. Okay,